Okay, so today we are very pleased to have Jamie Sikora from Virginia Tech, and he's going to speak about perfect quantum state classifications, balance, complexity, and nice examples.
All right. Thank you very much for a nice introduction, and thank you all for coming. I'm going to try to get that banner up. I lost my cursor. That's going to cover up every title of every slide.
I think it's okay.
Fantastic. Great. Figured it. Thank you. All right. Yeah. So I'm going to be talking about perfect quantum state classification. Oh.
Zoom is too careful. It is.
Please be careful. That's okay. Let's see if I can. Okay, sorry, 30 more seconds. Apologies. I lost my cursor for anyone. Just wondering what I'm doing here. All right. Okay, perfect state classification. So yeah, I'm going to define all the stuff that's going on there. But before I start, this is joint work with Vincent Russo, Unitary Foundation Psyquantum, Nathaniel Johnston at Mount Allison, and a new collaborator, Benjamin Lovitz at Concordia. It's based on these papers, and there's going to be a couple new bits that I mentioned here and there. Okay, so here's the plan. I'm going to spend a chunk of the time talking about anti-distinguishability. I'm going to define what this means. Then I'm going to open up the problem to classification. And if I have time, and I suspect I will, but we'll see, I'll talk about the complexity of this problem. Okay. But just kind of give you a glimpse of what's happening is that we started working on this anti-distinguishability for a while. Ends up, it's actually just a small part of a much bigger problem. Okay. Refer to classification. Okay, so let me talk about the problem. All right, so this is state discrimination. You folks have probably seen this in some capacity, but all right. Let me talk about kind of the setting and get that sorted out. So Alice is going to have two states, okay? And what she's going to do is prepare a qubit in either the 0 state or the 1 state, okay? And then she's going to go behind the curtain, prepare one of them, and send it over to Bob, like this. And the question is, can Bob distinguish the two states? Okay, so can you learn exactly which state was it? So just to do a sanity check, Alice is going to send, the physical state, okay, a physical qubit that is encoded in either 0 or 1. Okay, she's not sending, a picture with ket 0 on it or some vector representation. She's sending the actual physical state. All right. And the question is, can Bob learn which of the two states was sent? And it turns out, yeah, if he just goes ahead and measures it, he can figure out whether it's 0 or 1. Okay. So if he gets 0, he knows it was the first state, and if he gets a 1, it was the last. Okay. Is this clear so far? Any questions about what's happening, the setting, or? Yeah.
But it's always note that Alice will prepare two states.
Yes, thank you. I forgot to say this. So these two states are known. Bob knows what these two states are. I'm going to change the states in a second, but so actually, here's another example where it's a 0 and plus state. But Bob will know these two states as well. And so all this stuff is known. What's not known is when Alice goes behind the curtain, we'll prepare one of them. Which one is perfect? And that's what Bob has to guess. Yes, very good question. Okay, so let me go through this example. Pause again for questions. So you have Cy going over to Bob, okay? And the question is, does Bob have any hope now of learning what was sent? Okay. And at the end of the day, it kind of depends on how you define hope. Really, but if we want to talk about perfect distinguishability, okay? This is only possible if these two states are orthogonal, in which case these two states are not orthogonal, So, I mean, Bob could always guess with some probability. Okay. I mean, if he randomly guesses, it's 50-50. But there's some probability. But in this talk, we're always going to be looking at perfect distinguishability. So in this case, no, you cannot perfectly distinguish these two states. Yeah. Any other questions about kind of the setting, operationally, what's happening, or the fact that these have to be orthogonal? All right. If you have any questions, just shout out. Lots of time. All right, there you go. Orthogonal states are distinguishable. Probably already knew that, but now we have the context. So now we're going to talk about anti-distinguishability, which is a newish term. It's been around for maybe 3-4 years now. But before that, I'm going to talk about quantum state exclusion. Okay. So now Alice has n states here. Okay. Bob knows what those states are. Alice is going to prepare one of them, say psi I, send it over to Bob, and now the task is different. Instead of identifying the state, he has to rule out a state. Okay, so he has to guess a state that was not sent. Okay, and also by not sent, we can think of it as exclusion. So let me show you the cartoon. And yes, this is a completely different task. So psi 1 is sent over to Bob. Bob, in general, what Bob typically does is perform a measurement to generate his guess. So he measures the state. And right now he's going to say, that's not psi 2. And he'd be correct. Okay. So conceptually, this is an easier problem. Okay. Guessing a state. I mean, if he randomly selects a state now, it's with high probability, it's going to be correct. But what we care about in this talk is when you can do this perfectly. When you can perfectly pull it. So that's this anti-distinguishability. It's kind of a new term. All right. So a set of states is called anti-distinguishable. Okay. When Bob has a perfect strategy for guessing a state that was not sent. And just to compare, distinguishable, and by that I mean perfectly distinguishable, happens, I mean, the definition is when you have a perfect strategy that is zero error for guessing the state that was sent. Okay, so the distinguishing words here is anti and not sent instead of sent. Okay, is this new task clear? How you want to exclude a state? Anything funny? So the thing is, we understand distinguishability. Okay. In fact, it's kind of boring. The states have to be pairwise orthogonal, and this holds for mixed states as well. Okay. So we understand distinguishability, and it's boring. What can we show about anti-distinguishability? And is it also boring? Hopefully, I've convinced you it's not boring, but so here's a nice example. You folks may have seen this. Sometimes they're called the trine states. Okay. So look at the 3 states here, and you can imagine this picture is a little bit ambidextrous. You can imagine this just in Euclidean space, like this x is ket 0, and this is ket 1. Yeah. Then these things are just separated by, yeah. Anyway, yeah, some degrees there. But they're equally spaced out. Okay. This picture also works on the block sphere if you want, if you prefer thinking about block spheres. But those are 3 states. They're not orthogonal. Okay, they're not linearly independent because you have 3 of them in 2 dimensions. But you can always rule one out. Okay, and the measurement here is if you look at the perpendicular, you take perpendicular to each state like this, and you can form a POVM from these perpendicular states. You have to scale them down, but that's okay. And if you do that, you'll always be able to rule out a state. Okay. So these trine states have this kind of hidden property I didn't know about. If this was a block sphere representation, you could take any great circle and then the orthogonal thing is just the anti-portal point. So that would change. Okay. So here's the first main question. If I give you a set of states, can you decide if they're anti-distinguishable or not? Okay. And it's a yes/no question. I mean, the decision version, here's a set of states, yes or no, anti-distinguishable or not. Okay. And I mean, okay, so at the end of the day, it comes down to the existence of this special measurement, okay, this anti-distinguishing measurement. But maybe we could also ask, is there an easy way to tell if they're anti-distinguishable? Okay. All right, so let me pause and just emphasize this thing. Does this question make sense? Okay, so let me talk about actually what we do. All right, so our work started back, this paper, I think is 2021 or 2022 or so. Oh, no, sorry, it's a little bit earlier. I'll get to the year. So you have n states living in n dimensions, okay? And they conjectured, okay, that this is anti-distinguishable if the all the inner products are small, okay? Now this number is less than 1. I mean, it approaches 1 in the limit, but still, as long as they're small, that's what it is. And this is a really interesting conjecture. For one thing, we don't know how to characterize anti-distinguishability. Okay? Recall distinguishability, they have to be orthogonal. Okay, and orthogonality is it's a property of inner products, but there's no reason to think that inner products is the end of the story for all distinguishing tasks. Okay? But this conjecture says that, at least this is a sufficient connection. Okay. So the question is this true? All right. So now this is where I started chatting with my friend, Vinny. Okay. You got the reference? Okay.
I really want to picture and send it to him.
He's seen this. It's okay. There's nothing here. Okay, so here's a conversation we had in 2019. So that's about when this paper came up. So we're having lunch, and we're trying any interesting problems. And I said, well, there's this really interesting conjecture I read in this paper. Okay. And he's like, yeah, it sure does look interesting. And that was our whole conversation. We didn't really pursue it much. And then in 2021, a couple years later, get an email from Vinny. He's like, hey, are you still alive? And maybe some of you folks got these emails. Anyway, yeah, so we didn't talk for a while. Something happened. Okay, and then he also said, by the way, I left my computer running for 2 years and found a counterexample to that conjecture, which is one way to do it. To which I responded, what conjecture? I completely forgot we had this conversation. So anyway, we wrote this up in a little tiny PRA paper. Okay, there exist 4 states living in 4 dimensions. The inner product is this is the largest inner product, about 645. Up here, if you stick in n equals 4, you get 2/3 upstairs. Okay, so it's some margin below 2/3. And it is not anti-distinguishable. Okay, so they're sufficiently spread out, but you cannot anti-distinguish. So I'll tell you a little bit more about what's in this paper, but it is really, really tight. It's basically these 4 vectors and some quick proof, which I'll talk about right now. I'm not going to dwell on this too much, but there's something called a semi-definite program. And this is a way to optimize over quantum objects, broadly speaking. And one thing you can do is decide whether a bunch of states, I use mixed states here. It works for mixed or pure. Whether there exists a measurement that is going to have the properties. So right here, if I were to give you rho I and you guessed mi, this would correspond to a incorrect answer. And if you add them all up, that would be the sum of all the errors. Okay. So anyway, let me just kind of paraphrase. We have a very efficient computational tool to tell if they're anti-distinguishable or not. Okay. So at the end of the day, if we solve that and it equals 0, then it's anti-distinguishable, and this is an if and only if. Yep. However, you can't write a paper and just say something doesn't equal 0, because computers have a really hard time telling if something is 0 or not 0. Okay. I mean, for all we know, it's like 10 to the minus 92 or something like that. And the computer won't, I mean, at least the way we're doing it, we would not be able to distinguish that from 0. So there is a way to kind of certify this thing as positive, and I'll briefly mention that. But the question is, yeah, can we use this STP to prove anything? So let me talk about this totally legit algorithm. Okay. Well, pandemic, generate these 4 states, calculate the maximum overlap, okay, calculate the STP value. If number's good, stop and write a paper, okay? And this is exactly how we found our counterexample. And to prove it was non-zero, okay, the STP can give you something called a dual solution, and it serves as a certificate. So there's just a small write-up there just saying, hey, look, and this is also numerically found. All this stuff is numerical. Okay. So, and these vectors were ugly because they're given by MATLAB. And the dual solution is also ugly, but it did the job. Okay. Yeah, that's me when I heard the news. Yeah. Okay, so Nathaniel Johnston. So he came and looked at this. Okay, so let me actually say a little bit more. We try to clean up these numbers. You know, sometimes you stick them into websites and do these reverse symbolic calculator thingies, and maybe it's like, you know, arccos pi over 7 or something funny like that, where you don't readily know the decimals. You know, we did some fiddling around, polishing, but the numbers weren't talking to us. Nathaniel Johnston, however, looked at the paper. So 15 minutes after we put it on the arXiv, he found a better example. He's one of these people who can look at all these numbers and make sense of them. So he brought this number down quite a bit. Yeah. And he also generalized it to 5th dimension. So he figured this all out. Okay. So yeah, we all teamed up. I love this picture. Either I get a chuckle or it's just awkward silence. Yeah, it's fantastic. So I'm like, okay, we are now seriously working on this problem because we have all these examples. And yeah, so that was taken at our last group meeting. Yeah, and we're going to try to figure out this problem, anti-distinguishability. So a couple things that we're able to show is that we kind of have this kind of a corrected version of this conjecture. Okay. So if it's still a function of the inner products, all right, but it's a different function. Instead of the mole being small, it's this kind of, you know, this collective version of the mole beings. So if that thing, yeah, so, okay, let's say inner product small enough, then it has to be anti-distinguishable. Okay, there always exists that measurement. And a corollary, okay, if we want to state in terms of this conjecture up here, if all the inner products are less than that thing, okay, then it is also anti-distinguishable. Okay. If they're all small, then this kind of thing upstairs will be small as well. Okay. And we could show that this is tight. Okay. So you cannot, this thing here, you cannot bring that up any. If you put a plus epsilon here, okay, you will be able to find a set of states that is no longer anti-distinguishable. Okay. And that doesn't matter what epsilon, you can be as small as you want. So that is the tightest bound you can get. And downstairs, we're able to prove it was tight for n equals 4. And this number, whenever you stick in n equals 4, I believe you get 1/√3, which is about 57-ish percent. So we're able to show that that is the tight bound. But for n equal 5 or larger, this problem gets really tricky. Okay. And the short version, we weren't able to show it. The longer version is, well, the best thing you can do if you can't prove something is convince yourself that no one else can prove it either. So we convinced ourselves that this is related to some open problems in algebraic geometry. But that wasn't arbitrary. I'm gonna okay, so here's a related problem in algebraic geometry. Okay, so this is very similar to vector packing problems. Okay, so here's a really nice problem. Okay, and this is something you can think about in your head. If I just give you n vectors and d dimensions, and let's say they all have to have inner product gamma, or you could ask the same question, maybe upper bounded by gamma or something like that. The question is, can you find such vectors? Okay. I mean, if they're all orthogonal, or gamma equals 0, then n has to be less than or equal to d, right? But if you relax gamma to be positive, then maybe you can pack more vectors in. Okay, so this is very similar to our problem, but instead of packing vectors, in some sense, we're packing null spaces because you have all these orthogonality conditions. Okay, so we didn't nail this down exactly, but we convinced ourselves that we were treading very closely to some of these problems that have been open for years and years. Okay. So that was one direction. We're able to show that if the inner products are sufficiently small, then they have to be anti-distinguishable. We show the opposite as well. If a bunch of states cannot be anti-distinguishable if they're sufficiently close to each other. Okay. So if this function, this kind of collective function of all the inner products, if they're large, then there's no way to find an anti-distinguishing measurement. Okay. So this is the opposite. The other one said if they're all sufficiently small. Now I'm saying if they're all sufficiently large. A corollary of this is saying if they're all above this threshold right here, okay, which coincidentally is the bound upstairs in the conjecture that started this all. But if they're all bigger than that, then they cannot be anti-distinguishable. Okay. And this is kind of a nice way to think of it. Okay. We can also show that this is tight for all n. If you were to bring that right-hand side down at all, even by epsilon, then you can now start finding states that are anti-distinguishable. Okay, so that is a tight right-hand side. And downstairs, this is also tight. Okay. If you bring that down even by epsilon, this will no longer hold. Okay. Probably a good time to pause and ask if there's any questions. Okay. These make sense?
Just to clarify, the sum is over all i's and j.
I believe so, yeah.
Okay.
Yeah, so that whenever I is equal to j, these are all equal to 1.
Right.
So I think I counted for that, yeah. Okay, so it turns out these trine states are actually an optimal example for both bounds. Okay, so this is going to saturate the previous bound right here. Okay, anyway, the lower bound. So if they got any further apart, then they will no longer be anti-distinguishable. Sorry, closer together. Yeah.
Sorry, for the corollary, is there like immediate intuition? Because that's also like the same form that showed up in the conjecture, right?
Yeah, and I have no idea why. We asked ourselves why, but okay, this is a little bit different. They're saying like if they're all below this,
Yeah.
and this is they're all above.
Yeah,
So
just that figure. I was wondering why the conjecture did.
I have no idea. Yeah. I mean, the reason they had their conjecture is they did their own numerics, and that was the best they could find. You know, and they tested very different values of Van and all those things. Yeah, I mean, Vinny left it running for 2 years, so can't compete with that. He lives in Canada too, so he doesn't lets it run in his basement, warms up his whole house. So, yeah, so it turns out that this is an optimal example. So this is kind of a nice iconic example. I'm going to shift gears and talk about classification. It's kind of rip the problem wide open, but any questions about anti-distinguishability?
I'm just curious if you were to consider a general case where you're looking at a squared and you have evenly spaced points around the circle. So for
Yeah.
greater than 3, does that also give you like optimal examples?
I think so. These optimal examples, they have this property. Okay, let me try to remember. Okay, I'll tell you, and then I'll unpack it. The Gram matrix is circulant, so that is what characterizes it. The optimal examples have this property, and circulant matrices also have this property that there's some unitary that you start with a reference state, a periodic unitary that you keep applying unitary and it maps back after n iterations. So it has this special symmetry. So the short answer is I think so. I think there's a way to generalize this to have this special symmetry, like an orbit of some degree in unitary. But yeah, I'm not quite sure. We weren't able to nail that down. We envisioned a lot of these things, but yeah. There's going to be some more symmetric examples that pop up later for classification. So yeah, it's a great question. Any other questions? All right, so now I'm going to talk about classification. Okay, so classification will look something like this. So this is a classical example. Okay, so Alice is going to send a picture of a dog to Bob, and Bob just has to say that's a dog. Okay, he doesn't have to say that's a yellow dog or it's a Labradoodle or it's a that's Ben the dog. He just says dog, and he'd be right. Okay, so this is a very kind of classical machine learning task. Okay, or maybe you just get some kind of an email, and then you just have to classify it inbox, junk, or whatever. Yeah. So here's the quantum version of this. Alice is going to prepare a quantum state, send it over, and well, okay, suppose Bob just goes in and guesses what the state is. Side 2. And Alice is like, nope. Bob is sad. So he's like, no, actually I meant side 3. I misspoke. Nope. Okay, Bob's sad. I meant side 1. And then yes. Okay. So k-learnable, which is a new definition, we just made it up. And this is a set of states called k-learnable if you can always guess the state with at most k guesses. Yeah.
Interactive k guesses.
Does it matter? I don't think it matters. So actually what Bob is going to do is just spit out k guesses. And as long as one of them is right. Yeah. And I don't think there's a difference whether it's interactive or not. I mean, the way the cartoon is, it made it sound like it was interactive. Because he was trying to guess, and it was kind of softening the one setting to the other setting. But as long as you could imagine Bob just saying it's 1 or 2 or 3, and he'd be correct. Yeah. So just a little bit more about this definition is that if I give you any state from the set, okay, you can always narrow it down to k without error. You'll never be wrong. Okay, so this is still the perfect classification summary. Any questions about that? K guesses, no error. Okay, so let's first tie this back to anti-distinguishability. If I'm guessing a state that it's not, that's the same as guessing n-1 states that it could be. Okay, there's a complete, it's just a different interpretation of your guess. Yeah. So anti-distinguishability is just n-1 learnability. Okay. And perfect distinguishability is 1 learnability. You have to be perfect and you have 1 guess.
And just clarify with the learnability definition, we're assuming Bob just makes a single measurement and then
Yes.
makes those guesses.
That's exactly it. The single measurement and the measurement outcome is going to be a subset of size k. Okay. So going back to trine states, I said they're anti-distinguishable, but in this new perspective, it's 2 learnable. You can always spit out 2 states that were sent. Here's one that is 2 learnable, but now there's 4 states. Okay, so this is 0, 0, 1, 1, plus, plus, minus, minus. If you measure the first qubit in the 0, 1 basis, okay, then you can rule out one of these states. So suppose the outcome was 0, for an example, then 1, 1 could not have been sent. And after you do that measurement, you measure the second qubit. I mean, you can do it at the same time if you want. Measure the second qubit, and suppose the outcome was a plus, then minus, minus was not sent. So each one of these measurements rules out a state. So, if the first one is 0, the second one is plus, you've narrowed it down to 2. And you can always do this. I mean, 0 and plus with this examples. Okay, so that's Richard Cleave, if you haven't seen him. So last time I gave this talk was at IQC, where Richard hangs out. And he asked me this question. I thought it was very interesting, so it's on the slide now. So he said, a generalization of the trine states. So instead of having 3 vectors that are equally spaced out on a 2 sphere, a circle, what happens if you have 4 states equally spaced out on a sphere? Okay, so we call these tetrahedral states. This is the best ChatGPT could do. I couldn't do any better. Mine looked like a triangle. Anyway, so yeah, I'm going to explain the picture because it's not that good. But you have a triangle-based pyramid, okay, completely circumscribed inside of the sphere. Okay, and those 4 points are touching the sphere. These are the vectors if you prefer to see that. Okay, so these are not distinguishable. Okay, you have 4 of them living in 3 dimensions, so they're not even linearly independent, let alone orthogonal. But are they anti-distinguishable? Yeah. And then I thought about it for a while, and yes, they are anti-distinguishable, so that's cool. But then it turned out that these are actually 2 learnable. Okay, so if I give you one of these 2 states, you can always narrow it down to 2 of them. So in other words, you could either narrow it down to 2, or you could rule out 2. Okay, that's another way of thinking about it. So okay, and maybe I'll just emphasize that I thought this was quite interesting because they're not orthogonal, but you can still perfectly learn something. Yeah. Yeah. Then I told him. So this is our anti-distinguishing bound. Okay. They cannot be anti-distinguishable if this function of the inner products is large enough. So here's a generalization. Okay, so this one's on the arXiv, this one's not on the arXiv yet. But yet n states cannot be k-learnable if you have this function right here. Okay, I have a laser. Okay, so this n-1 is really k in disguise. Okay, so that's I mean, not every n turns into k, this n stays at n. Okay. But this is about as nice a function of n and k as you can imagine. Yep. So we're able to show that, and we can also show that this is tight for all n and for all k. So it doesn't matter how many states you are or what kind of degree of learnability that you have. This is going to be tight. That is, if you make this an equal sign, this can be k-learnable now. So yeah, so we generalized that bound. This is our bound for the lower bound if they're all small. then they have to be indistinguishable. And this is a conjecture. We haven't proved this yet. But we have strong evidence to believe that it's k-learnable, okay, if all the inner products are small, and that's how small we need them. Okay. So right here, this generalization is kind of funny. Like this 2 actually, encodes n and k. But again, like to go from here to go back upstairs, indistinguishable means n minus 1 learnable. Okay, so this does generalize this stuff. Okay, and this is true and tight for some examples. Okay, so when k is equal to 1, this is 1 learnable, which means they have to be orthogonal. And if you just put that in, kind of stare at this for a while, you'll realize it has to be orthogonal. All the I not equal to j entries are forced to be 0. N minus 1 is true and tight for the same reason as upstairs. Okay. But 2 is new, okay? And we're able to show this for 2 learnable. Okay. For other values of k, this gets quite tricky. And then maybe at the very end, I'll circle back. I'm going to talk a little bit about how these things are proved and some of the sticking points generalize this. But yeah, we verified this numerically. We have examples. That's k-learnable that saturates this bound. So, and they're really nicely constructed examples, but almost. Yeah.
So when you say like conjecture, you mean that like you've showed it for all?
We've shown it for those values of k.
Okay, but it's conjecture for the other.
We conjecture for all k. That's right. That's right. Yeah. Yeah. Nathaniel is 100% convinced that this must be true. And I mean, it'd be aesthetically pleasing if this was true. And it matches. We have 3 data points saying it's true. So it feels like it should be true. But I mean, stranger things have happened.
So what's your interpretation when k is larger than n plus 1? Does that mean that you won't have a k k-learnable when k is larger than n plus 1?
So okay, so the bounds on k is 1, which means perfectly like a orthogonality basically, and the upper bound is n, because if you have n states, you can always guess with n guesses.
Okay.
So you'd never go above n,
Okay.
Or at least I guess you could go above n. It'd be weird, but right here we're constraining n k to be less than n, which I think is fine. Yeah, we're not getting any division by zeros or anything weird like that. So yeah. Does that answer your question? Anything funny? Okay. Alice, yeah.
I think technically you could define this problem for k equals 0 or n, and this conjecture would still make sense in the same form. Like for 0, you would never be able to learn anything. For n, you'll always be able to do.
Right. I mean, everything is always n learnable. So as long as you have that should be true. And 0 learnable means
You have to return the empty set, and you always are wrong, I guess.
oh, I see. That's some kind of weird vacuous thing. Yeah. I mean that could work too. Okay, good. 2 more data points. So this conjecture is definitely true. Great. Okay, so I'm going to talk about 2 learnability in this second because we can actually prove this for 2 learnability. But any other questions about this? Yeah.
Just a curiosity. So you've is the missing part showing that it's tight for the other case, or are you?
No, we can't show either. Yeah. So we can't show. Yeah, if you stick in like say 3 here, or maybe n minus 2 is another thing we tried. If you stick in 3, we can't prove that this theorem holds in general. What we have are, I don't want to say too much because it's still, I mean, did it last week. But we have a really cool construction of a set of states that work for all the small n's and k's that we tried. And we believe that this is going to be an optimal example. So the tightness should be able, I mean, the tightness, if it were true, should be, we should be able to prove this. Like if you put in epsilon plus epsilon, then we can numerically find things that, but this is not going to hold. But we can't prove that if it's less than this. It has to be k-learnable. And just because you have one example doesn't mean it's going to work for all examples. So, yeah, it's super interesting, and we've been banging our heads against the wall. But I'll circle back why we can prove it for those and not other values. The short version is that we can connect this to another mathematical problem, and there's only so much progress made on that problem. So, yeah, and good questions. Any other questions? Let me talk about to-learnability. Okay. So to-learnability is the next best thing you can do if you don't have orthogonality. Okay. So orthogonality is one guess. This is two guesses. Okay. So the corollary from the things on the last page, it cannot be to-learnable if all the inner products are larger than 1 over n minus 1. And for some reason, we have the same bound for the same right-hand side for the lower bound. It must be to-learnable if all the inner products are less than that same number. So this is, you know, this holds because we can prove things about to-learnability. And the optimal examples for to-learnability is a generalization of the tetrahedral states. Okay. So what you can do is you can take n vectors and spread them out. My brain doesn't work in above 3 dimensions, but spread them out in such a way that they're in some sense maximally spread out. Okay, it's in some kind of symmetric way. And if you do that and you set all the inner products to be this, okay, and yes, like no phases or anything, so real positive numbers, yes, then you can prove. Okay, first of all, if you just set all the inner products equal to that, you can always ask, how do you embed these vectors? And you can prove that the minimum embedding dimension of those such vectors is n minus. Okay. So if you do that, then you'll have an optimal example. You have an optimal example for to-learnability. What else? Oh no. Okay, maybe that's good. Yeah. So yeah, we didn't know this before talking to Richard, and then he gave us this nice example, and it just opened it wide up. Okay, so now we have all this up. I forgot that was coming.
Richard this.
He's seen some variant of this stuff.
Okay.
Not that though. Okay. So now I'm going to switch tunes a little bit and just talk about how hard it is to decide the k-learnability. But any questions up to this point? Anything funny? Okay, let's talk about complexity. Okay, so there's something, I'm going to define it as learning. Okay, so if I give you a bunch of states, what you can ask, instead of asking yes, no questions, like is it 2 learnable or 3 learnable, I'm just going to say, what is the smallest k for which it is k-learnable? Okay, and this is going to be some kind of, you know, quantum information-y type quantity you can assign to this set of states. Is in some sense, it's how learnable. And you can show the Chine states of learning with 2. 2 is a particularly nice number because if you know it's 2, and then after that, you just have to check if it's orthogonal or not. And if it's not, then it can't be 1. So those things have learning with 2. Maybe I'll skip over that in the interest of time. So here's the decision version. Just decide if the learning, if I give you a bunch of states, I'm going to embed n states and n dimensions just to get around some kind of weird encoding things. Decide if it's k-learnable. Okay. Since I'm probably running out of time, looked into the future. So here's a kind of informal theorem. Okay, so the learning width, deciding whether it's k-learnable or not, is NP complete. Yeah. But it's NP complete when k is a part of the input. Okay, but if k is a fixed constant, then you can actually show you can solve in polynomial time. So let me give you a little bit of the reason why it's NP complete, okay, or at least NP hard. So this is exactly set up in the way Carl asked. What you can do is when you're given a state, you can form a measurement, and you have a measurement outcome for every k subset of n. Okay, which is, I mean, there can be a lot. Okay, so you have this measurement, PLVM, with lots of little matrices inside. But once you have that, you can calculate the sum of the errors. If this doesn't make sense to you, that's fine. But I'll point out that you can solve this. It's some definition of solving. Okay, let's just talk about computability. You can solve this. And really what you want to know is that if that SDP is 0 or non-zero, 0 or positive. Okay. Okay, so when k is fixed, this can be approximated efficiently. Okay. And I'll just hand wave this, but basically the number of variables, okay, MS here, is going to be the number of subsets of n of size k. And if k is a fixed constant, this is a polynomial. Okay. So this whole thing you can prove is polynomially sized, and then you can use STP algorithms to show that you can approximate the whole thing in polynomial time. But can someone tell me what happens if k is not fixed? If you wanted to solve such a thing, and there's n choose k variables, what happens if k is not fixed? See any problems? Could you imagine an input or a choice of k that would make your computer start crying? If k is about n over 2, okay, then you have a lot of subsets. Okay. Does anyone know how big n choose n over 2 is? Exponential. Exponential, exactly. It's exponentially big. Okay. And you can prove by Starling and bound, you get a close approximation that this thing is kind of like 2 to the n. I think there's a division by square root n, but so it's basically exponentially large. So that's some kind of hint that maybe you're looking at something that's NP hard. Okay. I mean, that's not a proof. If someone said that's a proof, run away. It makes no sense. So that's kind of a hint that it's NP hard. Let me talk about a little bit about how we prove these things. What we can show by looking at that STP is that if you have these n states, they're k-learnable if and only if the Gram matrix has a very particular property. And I'll talk about that property. It's called k-incoherence. I'll talk about that in a second. But first of all, the Gram matrix is going to be this big matrix. And this matrix right here is the collection of all the pairwise inputs. Okay. And there's no absolute values or anything. So these could be complex. Okay. But you gather them all up. So the point is that if I give you a set of states, determining if it's k-learnable is only a function of its Gram matrix. You only care about the inner products. Okay. So that kind of circles back to the first thing I mentioned, like what should characterize anti-distinguishability? What should characterize k-learnability? Turns out the only thing you really need is the inner products. Okay, so that's already kind of interesting. But the actual property we want is k-incoherent. And k-incoherent says something like this. An operator A is going to be incoherent if you can write it as or decompose it as the sum of BIs. Each BI is positive semi-definite, and it's going to have a lot of zeros. Okay, let me be more precise. Basically, the whole matrix is zero, except for possibly a k by k submatrix. Let me just give a quick example. So we argued before that that set of states was two-learnable. This right here is the Gram matrix, which again captures all the information that we need. The Gram matrix, like if you just look at the inner product between 1 and 3, you'll get 1/2. Okay. And you can decompose it as the sum of 4 objects. Each one is positive semi-definite, and each one has at least 2 rows and columns that are all 0. Okay. So in this case, you have this symmetric submatrix indexed by 1 and 3. It's non-zero, but the rest is forced to be 0. Okay. And this decomposition alone is sufficient to prove it's two-learnable. I didn't even need to go through the argument. I don't even need to show you what the matrix is or the measurements are. Okay, so let me just take 1 minute, wrap up here. So this is kind of, okay, and this if and only if proof is one big STP proof. You just fiddle around with STPs, which is something I like to do a lot. And you can prove this if and only. Yeah. But now that we have this characterization, we can ask the question, well, what's up with these k-incoherent matrices? Okay, so that's Nathaniel. He's coming back. Shortly after joining the project, he just realized, hey, these things, at the end of the day, we just care about the Gram matrix having this coherent type structure. And coincidentally, he wrote a bunch of papers on this. I don't know why, but he did, and I'm very grateful. And that basically gave us a recipe to prove things now. So I say all we have to do is study when the Gram matrix is k-incoherent, or n-1 coherent and all this stuff. I put those little star things because there's still lots of math to do, but this gave us a starting direction. Okay, and the results in his previous papers kind of left a trail of breadcrumbs. But maybe to get back to your question, he could only prove things for k-incoherent for certain values of k. So it turns out some of those values of k were really hard, and he couldn't prove them. Well, him and his co-authors, and that's why we're kind of stuck on some k equals 3 and 4 cases and stuff. Yeah, and that's kind of like the quick idea how we got our something. Okay, I'll introduce Ben real quick. That's Ben. So what Ben and Nathaniel were doing, they were looking at this k-incoherent matrices. Okay, kind of like a side project, if you will. And they proved that determining k-incoherence is NP-hard. Okay. So if I give you a positive semi-definite matrix and ask, is it k-incoherent or not? Turns out what you can do is if you could answer this question, then you can solve the k-clique problem. Okay. The k-clique problem is if I give you a graph and a parameter k, you have to decide if there's a k-clique inside that graph. Okay, and this is an NP complete problem. If the clique thing didn't make sense to you, it's fine. It's just one of the tens of thousands of NP complete problems we have. And that's exactly. And the reduction is actually quite nice, but I'm not going to go into it. Also, this paper showed up on the arXiv right before ours and also showed the same proof for different reasons. They also showed that k-incoherence is NP complete, and they turned out it had the same proof as well. So stars were aligning for people to be working on this. Okay, so yeah, it was basically peanut butter and jelly. We put our learning stuff together with this hardness of the k-incoherence matrix decompositions, and yeah, we get a result. Yeah, so Ben joined the party, and I'll wrap up. Thank you all for coming.
More questions?
So maybe a bit of an unrelated question, like what happens if you have more than one copy?
Yes. This is a subtle thing that I kind of glossed over. But if you're given, okay. Do you mean like what happens if psi1 and psi2 are the same? Is that what you mean?
Yeah. Yes.
Okay. I'll answer two questions and hopefully I'll get one of them.
Okay.
So if psi1 and psi2 end up both being, say, the 0 state, then really what you want to do is you want to guess the index of the state.
Okay.
So like kind of a boundary condition is if, imagine you have n states, but they're all 0. Then you might think, oh, it's easy. I can just guess the 0 state. It ends up, it's extremely hard because actually what you want to do is guess the index. So yeah. So, okay. So there's that thing. The other thing is, and this is something we're thinking about now, is what happens if you're given many copies of the same state. The more copies you have, the more distinguishable they become.
Okay.
So we're also looking at, certain sets of states. And then as you increase the number of copies you're given, how does it impact the learnability of the set? Because as you increase K, they'll become more distinguishable. And then we can show some kind of finite bound on K such that becomes 2 learnable.
Okay.
And this is some finite threshold, but they'll never become 1 learnable.
Right.
In the infinite limit, they'll become orthogonal.
Sure. Yeah.
But there's no finite depth. So yeah, it's super, super interesting and something we're thinking about. Yeah. Thanks for the question.
I'm curious if there might be any links to random access coding, because it seems somewhat similar.
Yes. So there's 2 learnability. From a 2 learnable thing, what you can define is a random access code, which is something I just made up as well. And what happens is that you can decode either the first bit, the second bit, or the XOR, but you can do it perfectly. But you lose the freedom in choosing. So for a random access code, you get to choose whether you learn the first bit or second bit, and then NAICS bound and all that stuff, and there's some bounded probability. Here you can do it perfectly, but you forfeit the choice. Yeah. And this is something we're still trying to iron out for other values of K, but for 2 learnability, it lines up perfectly. So that's a fantastic question. Yeah, we've read my mind. Yeah.
Other questions?
So what's the intuition between like K coherence? Like what does it really mean? My states. Or is like
I'm not quite sure. I mean, okay, first I'll say this is definitely a Nathaniel question. He loves coherences. But that's a cheat answer. If I give you a quantum state, let's say it's a mixed state, then a coherence is in some sense the measure of all the off diagonal items.
yes.
Right? And if they're all 0, then it's fully incoherent. And that's kind of also what we have going on here. So we have a matrix, look at the grand matrix. The grand matrix is going to be 1s on the diagonal. But now we're worrying about how the overlap of all the other states, which is all the off diagonal things.
Yes.
So coherence is kind of measuring how big all the pairwise intervals.
Yeah.
So that's kind of a rough idea, the connection.
Okay, thanks.
Yeah, it's a really good question.
So, well, then, not really follow the question, but it seems if I'm given like a set of states, where one of them has like a significant overlap with all the other states, the other ones are sort of don't have that much of an overlap, then that one is sort of the one being tricky.
Yes,
distinguishability.
That's right.
Right, and so if I allow myself a little bit of a leeway with that one. I think that's when I increment the learnability by 1. So it's not 1 learnable because that one has like a large overlap. So now I'm looking at 2 like learnables. That like the incrementing the K is to overlap, and so now I'm looking at the second highest overlap, right? And if that one is too large, then I'd have to increment the learnability again by 1. This is kind of the minimum.
That's right. Okay, so maybe if I could kind of offer a different perspective. If you have one state that's being kind of tricky,
Yeah.
One thing you can always do is just throw it in the garbage, ignore it, it exists altogether.
Mhm.
Okay, and this is basically achieved by taking all the POVMs, and if they involve that state, just set the POVMs to be 0. Okay, and just worry about all the the effect, the operator, and just worry about optimizing over the rest.
Mhm.
So instead of changing k, in some sense, what you're doing is you're changing n to n-1, but you can still ask for the same value of k if it's k-learnable.
Okay.
So all the tricky ones you could throw in the garbage. And you could play this game too. Like, what's the maximum inner product? I don't like that one. Throw it out now. I haven't thought about that. That's actually kind of a neat idea. But look at the maximum inner product of all the rest of the states. Yeah, like if there's a subset that's anti-distinguishable or k-learnable, then the whole thing is also k-learnable. I believe that's true. So yeah, so you can play these games.
Yeah.
Turns out to be quite fun. Yeah.
Seems it would make like things like very hectic once you.
I mean, if you want to turn it into a systematic or algorithmic thing, but yeah.
Wondering like, well, once you make it like not perfect distinguishability, it's just like will seem immediately out of the window, right?
Yeah. Yeah, it's fun to think about. I should also say I'm floating around the rest of the day as well. I'll probably be around Morrow's office. Is that the plan? So if anyone wants to chat about this stuff, I'm very happy to. I'll be floating around. So yeah. Yeah, thanks for coming, everyone.
Okay, good time for everyone. Thank you.